Welcome everyone to our first Research Tools Workshop series. The first, as I said, in a series of what is currently slated to be 5, but we're hoping will be more workshops. The purpose of these workshops is to introduce a tool that is available through NHERI SimCenter, and we hope moving forward through NHERI Design Safe. Directed primarily towards graduate students so that graduate students can get exposure to how to use these tools, some applications, and speak to somebody who is an expert or more familiar with those tools and have the opportunity to ask questions and understand their capabilities. This workshop has been organized through the tireless efforts of the NHERI Graduate Student Council. Myself, Rakesh, Jasmine, and Olani, part of the research and workshop and mentoring workshop groups, part of the NHERI Graduate Student Council. And in just a moment, I'll introduce our fabulous presenter and speaker today, Dr. Quanxi Zheng. Just to quickly introduce the NHERI Graduate Student Council, this is an organization that began about a year ago through a NHERI initiative to bring together graduate students. Our purpose is to build a diverse community of natural hazards researchers, connect with diverse mentors and diverse students across natural hazards fields, attend workshops centered around research and career building, encourage DEI, diversity, equity, and inclusion conversations, learn about the impact of research on practice in the natural hazards fields, and to gain leadership service and funding opportunities. This has been a fabulous experience for those of us who have been part of it, who have found leadership positions, collaborations, and other opportunities. And so if there are any graduate students here who are not a part of NHERI GSC who would like to be a part of it, or if you are not a graduate student, but you're interested in working with the NHERI GSC in the future, we have a QR code here, as well as a shortcut to our website to learn more and get involved. I'd now like to introduce our speaker and presenter for today, Dr. Quanxi Zheng, joining us today from Stanford University. He is a postdoctoral fellow at Stanford University's Bloom Earthquake Engineering Center and a member of the NSF-funded NHERI SimCenter. He received his PhD and Master's of Science in Civil and Environmental Engineering from Stanford University. His work focuses on the behavior and critical failure modes of reinforced concrete structures, surrogate modeling using statistical learning techniques, and methods for assessing and enhancing community resilience to multi-hazards events. He has published his research extensively in the fields of earthquake and structural engineering in journals such as Earthquake Spectra, the Journal of Structural Engineering, Earthquake Engineering and Structural Dynamics, and in the proceedings of multiple national and world conferences of earthquake engineering. Today, he's going to introduce the EEUQ tool as part of SimCenter, discussing his work on structural analysis from seismic events. Thank you so much for joining us today, Dr. Zheng. I'll now turn things over to you and stop sharing my screen. Before I do turn things over fully, though, I would like to urge that questions be held to the end following Dr. Zheng's presentation, unless it is an immediate clarification question or needing something to be repeated. And that way we have ample time to get through the presentation and ample time for questions at the end.
And thank you so much, Ty. Thanks for the warm introduction. And thank you, Robin, for offering the chance and inviting SimCenter to join this GSC presentation series, workshop series, to share some of our research experience and specifically in our own research fields. And this time I have some prepared slides and want to just share some of my experience working in the earthquake engineering field and specifically using the SimCenter EEUQ tool. And actually, just let me just start to present here. Yesterday, I was trying to collecting and preparing a set of slides that for today's talk, but the first thing I come to my mind, I don't know how many of you actually look into the websites frequently, tracking how many earthquakes actually occurred in the world and even in the Bay Area. So I just went up to the USGS website, which you can see at the link below. And I just type in to see how many earthquakes in the past months, and it tells me even for those instrumented earthquakes that we really identify from our earthquake station are really close to 10,000 here. And if you look into how it's really distributed, it's kind of like we have really dense cluster in Alaska and a lot of in the California Bay Area here, which if you overlap our population map, you will see, okay, we do have a lot of people living in this region, which will be potentially affected by those things. And but the good news is that sort of if I plot do a little bit of statistic, try to see what's the earthquake magnitude and plots the histogram of the earthquake magnitudes here, you will see 90% of the earthquake actually below magnitude 4, only 10% in the past months actually exceed 4. So maybe those small earthquakes, we even do not really feel it. Like a few weeks ago, there's an earthquake in Bay Area, and one of my friends actually got earthquake early warning, but myself, I did not really realize that. It's about magnitude 5 here. But then for those small number of large events, we still need to really study the earthquake because they have really large and significant impacts in our society. And look back enough, even far away, just 10 years ago, Japan, Tohoku earthquake, just this, some striking figures I just requested from the Asian Air Survey company, just for demonstrating that how badly the earthquake can influence this local community. And on the top left, you can see the Sendai Airport, which is the large hub of many international airlines, just got fully damaged and inundated by the tsunami following the earthquake. And you can see also the infrastructure lines like the bullet train, Japanese Shinkansen, also derailed during the earthquake. And you also see some transmission lines on the railway actually got really damaged, including another disaster on the nuclear power plants, which is currently still under addressed, not fully addressed yet. So this is kind of like a big event, but not even a magnitude 9.0 event can cause those problems. Even a magnitude 6.2 events that happened in a really populated region can cause a lot of aftermath. So one of the unfortunate example is that 2010 Christchurch earthquake magnitude 6.2, which really caused a few number of structures collapse. But the problem is that if you look into the right figure here, which you could see the blue color shows the closed region that's due to the certain structure damaged. Not all structure have been decided to be closed and then not valuable for occupancy, but your structure actually influenced by your nearby structure, which can be potentially damage your safety as well. So this sort of the corner effect after the earthquake, after the major earthquake will also influence the local recovery from the earthquake disaster. And the economic loss and will be really substantial if you really close the central business district for even 2 years. And a big statistic that just gathering from UN Office of Disaster Risk Reduction, looking into the past decades and the total number of deaths, the earthquake is attributed for close to 58% of the total fatality from the natural hazard. And on the right-hand side, if you see the breakdown of the economic loss in US dollar in the past decade, still number 3 is earthquake, 20%, 21%. And looking into Americas, it's about $1.32 trillion, which I would say in US, it's kind of like a close to 70% of the total number. Then I really want to say, like as an earthquake engineer and structural engineer specifically, what our goal to study earthquake and what's the ultimate goal that we are pursuing for is really by studying earthquake, we can mitigating the risk. And I will show you 2 really effective examples that structural engineers learn from past earthquake disaster and make the change and do study the earthquake features, the structural responses, performance analysis, find out the problem, and try to improve the design, and finally really can help to save our community from the disaster. And one of the example is the Northridge earthquake. During 1994, Northridge earthquake actually bring a lot of damages to the steel frame connection. So you will see here, horizontal is steel frame beam, and a vertical is a steel column. And the earthquake itself did not really collapse the structure, but when structural engineers stepped into the building to do the inspection to decide whether the building is safe to occupy, they found that actually there's a lot of cracks here, ruptures between the connection. That is because the design did not, before the earthquake, did not really consider the potential stress localization at the connection level, which will really fracture at the welding points. And after the event, structural engineers design and developed this new type of the connection, which we call bed jog bunker. Here, you will have a weakened section before your the beam join the column. So all the force will really concentrate at this yield the section instead of concentrated the strength at the weld level to reduce the potential of the steel fracture there. And another example, just in San Francisco, about the SelfDestory program in the wooden building. And what is SelfDestory? The bottom left figure shows you an example that we have a wooden structure, and the first story typically is not as stronger as your massive residential mass on the top of that, and under earthquakes it tends to have a story mechanism and have a local collapse. So you really cannot use this building and even go into the top floor to access to your personal belongings, and this is actually quite a big problem for the county, for the city. Here you can see on the right top figure, you will see this identified SelfDestory at different vulnerability levels, and but through the studying that structural engineers try to really target those weak building and build detailed model to analyze how bad the structure would behavior and what would be the potential retrofitting strategies and affordable strategies specifically for those low-income families in the city to retrofit their weak building. SelfDestory here. So it's kind of like an ongoing effort that's led by California Earthquake Association to really push this ahead to help us build a more seismic resilient community. And those sort of the goal of our structural engineers in earthquake studying. And just one big picture of the commonly used methodology that also will be also our SimCenter tools are built on the top of this concept called performance-based earthquake engineering. And the goal for this methodology is really to assess the potential natural hazard risk and their impacts on the built environment. And the risk itself actually consists of three components, from hazard to exposure and the vulnerability. And the performance-based methodology basically is a quantitative analysis methods for earthquake hazard to built environment. And starting from the infrastructure information, for instance, I have a bridge here and located in the Highway 101 in California, and I have its location and design parameter. I look into the earthquake national hazard map and try to find out the hazard, the ground motion intensity, which I will introduce later in the presentation to the earth, which basically describing the earthquake shaking intensity. And that the structural engineer to build a structural model and analyze the structural behavior and try to assess its possible damage under the different earthquake intensity levels. And finally, to develop what could be the potential loss from 100-year period, consider all possible earthquakes and help city managers and building owners to make a better decision to improve their design and protect their own buildings. And starting from the header, we need to first look into the earthquake characteristics, which really is the source of all the aftermath or the disaster we'll see. The ground shaking intensity really depends on three things: earthquake source mechanism, propagation path, and the local soil properties. And for the earthquake source, I just show a really nice figure below, which I just borrowed from one of my colleagues. This is one earthquake fault that the earthquake seismologist model for Hayward fault, and which is in the area here, close to San Francisco and Auckland. And you will see the fault itself kind of like a rectangular plane underneath the ground, but you will see a lot of different colors here, which shows the earthquake slip, fault slip, which means that if you look into two planes, earth crustal planes, they will move relatively to each other, and the color just describes how much they slipped away from each other. And this slip will really release a lot of energy, which will transmit through the soil layer, the crustal layer of the earth, and towards the surface, and finally generates the earthquake ground motion, which we can feel on the ground, like in the building shaking. Well, during the transmission, the earthquake seismic wave actually is also propagated through the entire crustal structure, and any different soil properties will influence the final delivery of that earthquake shaking at the ground level. One famous example is looking to 1985 Mexico City earthquake. And the earthquake itself is really far away from the Mexico City. Well, the earthquake seismic wave passed through the entire soil structure when it arrived at Mexico City, which has a large basin. The shaking actually amplified at a certain period range. You could see here, if I plot the shaking intensity at the edge of the basin versus at the center of the basin. So you will see that even from this seismic wave format, you will see that the amplitude got really amplified. So this uncertainty needed to be considered when we analyze a building structure or infrastructure to assess its potential damage. And this will be really later introduced in our EUQ2, which you can really consider those systematically. And when the earthquake seismic wave arrive at the ground level, it typically will be showing this time wave format. The x-axis is the time domain, y-axis is the acceleration recorded at the ground level. So you can see this is the top figure showing one records recorded in the north-south direction, bottom is in east-west direction, and a little bit scale. And if we look into how to describe this ground earthquake shaking, we'll see, okay, we just pick up the peak value in the time history, which are the peak ground responses, peak ground acceleration. For instance, I just read the maximum value from these two figures. I could also look into the time domain to see, okay, what's the duration of this earthquake ground motion? And I can also look into different features that embedded in this wavelet, like the pulse-like and fling features. And on the other hand, if I look into the frequency domain, I can have a response spectrum, which tells me if I have an elastic single degree of freedom on the top of the earthquake records, what would be the peak responses of that, and converts that to the pseudo acceleration here. And I will dive into a little bit about the detail later in the two. Finally, we have the earthquake records. We want to analyze the structural responses and potential damage. And here, one very important terminology is called nonlinear response history analysis, which is heavily and commonly used in structure engineer daily practices. Just a lot of benefits coming from this methodologies that we can directly estimate the displacement demand of the structure, and considering the elastic response history and the damage, quantify the potential material deterioration and those path-dependent failure modes. And it's also a recommended methods in many building design standards and the code, and for new structure designs, for retrofitting, for seismic upgrade, and assessing the performance, and calibrating the code design criteria in the FEMA standards. And I don't want to really bother you too much about the methodology itself or how, but want to show you one quick example of how really one of the design firm perform this nonlinear response history analysis in their structure design, building design. This is one of the peer tall building initiation project, 42-story concrete wall building designed by MKA, which is a very famous design firm in the world. And the building site itself is located in downtown LA, and it's controlled by the local nearby earthquake from southern San Andreas fault and the Elisha Park earthquake. So you can imagine that there's a chance to occur really up to magnitude 7.9 from the San Andreas fault and the 6.6 from the Elisha Park. And the building is actually controlled by the seismic design itself. And the structure engineer first developed the seismic the designs drawing, and then try to build the model in this numerical software. And the building itself has a fundamental period of the first period 4.6 seconds in east-west direction, 3.5 seconds in the north-south direction. And the design-based share following the AAC model analysis methods is about 4,500 kips. In the bottom, I'm just showing some of the snapshots in their design document. And what the structure engineer do following that is try to get the target response spectra, which describe the earthquake shaking at the building site, and try to find out what are the representative earthquake ground motion that can be used for analysis, and they use those records to do the time history analysis and understand what would be the maximum story drift ratio along the building, and what would be the wall shear to help inform and optimize the design. And this process typically are iterative. In reality, structure engineer tends to push the structure to balance the structure safety and the building cost to deliver the optimized solution for the owner. And just to abstract that process a little bit, starting from a structure design, and try to build a numerical model for the structure, and then obtain the structure response spectral targets, selecting ground motion, and try to fit the response spectra. And once gathering that structural responses and ground motion information, and we start to get the analysis go to analyze the structure and finally check the responses. And if that's fulfill our targets or performance, or then we can go with that design. If not, then we will loop over and do another cycle to iteratively design and optimize the structure. And you will see there's a lot of steps, and many different softwares will be involved. For instance, you will design the structure and having the drawing in AutoCAD, and then you will build the model in different softwares. For instance, ETABS, Perform 3D, or you can build that in some academic softwares, OpenSea is called. And then you perhaps will use different websites and APIs to get the target response spectra, ASC 7 standard, or you can go to USGS to do some uniform header spectra, or you can use different software MATLAB codes that are published by different researchers to calculate the different target, like the conditional spectra series. And then after which you can select the ground motion from peer JOS database, or you can do some other local selections if you have the ground motion records from other resources. Well, I want to mention that the today's talk mostly around the EEUQ application, it's sort of a tool that can help you streamline this entire process, and it's leverage different softwares and bring them together to a front end so you can interact with the EUQ software, and in the back end, all the different software that you need will be called in the sequence and help to solve this problem. And the EUQ itself is a short name for Earthquake Engineering with Uncertainty Quantification application. And this is based the one of 7 different research tools in SimCenter to help predict the response of a building subjected to earthquake events, and specifically want to look into and quantify the uncertainty in predicted responses. And just to have a quick list of the 2 websites, 2 documentation, and a lot of resources you can find also through our SimCenter forum. But don't forget to register a Design Safe account to get the remote HPC resources, where you could put on the analysis to the high performance computing resources to run analysis in parallel. And before diving into the tool, the use page, we want to have a very quick slides just about the ground motion selection and scaling, which will be demonstrated later, just in the next slide. Just to have this quick slide that why we needed to really do this ground motion selection and what would be the criteria. The reason for ground motion selection is because we want to get a subset of earthquake ground motion records to represent the building site's seismic hazard, and that we could analyze the building, how they perform under the local events. And ASC 716, which has a list of the recommendation on ground motion selection. And I will not really dive into them one by one, but one of those very important key criteria is that the ground motion should have similar response spectra shape to the target spectra that you obtained from ASC 7 standard or an other recommended response target. And specifically, it mentions that in over the period range of 0.2 T1 of the structure to 1.5 T1 of the structure, the response spectra, the mean of the selected response spectra should not really below the 90% of the target response spectrum. And in EUQ, the ground motion selection is really handled by an event panel. I will just open the application for you now, so you can see the page where I'm talking about. So this is the EUQ application. And if you go to our website, which is here, that's in the earthquake I just copy this link in the chart. If you like, you can just click through to open that for now. And then you can click on the download application, and inside this folder, you will see the latest version. If you want to use the earlier version, you can also click into the old version. We have all the archived version there for your interest. But then when you download this application, it will going to be a zip folder, and unzip the zip folder here, you are getting a directory that in which you will find out executable called EUQ. And once you open this, you are getting to this page here, which is the landing page of our tool. And on the left-hand side, there's a lot of different functionalities, and the RIPS, we call it RIPS, like UQ is the uncertainty quantification, GI is the general information of my project here, and the same is the building model generator, the structure information model, and the EVT is today's talk focus, that's the event panel, and I will come back to this quickly. FEM is the final element. You can select different engine to do the analysis. EDP is the engineering demand parameter, which is structure, another name of structural responses, like the displacement forces and the acceleration demands in the building. And the random variable that if you want to include the uncertainty in your structural model, the material that you use to build your numerical model, you can include it here. Okay, let's back to the event here. So in the event panel, well, basically to describe how we would select the ground motion to our target response spectra. So on the top left panel here, you will see a target spectra, under which you have different options. You can go to AC 710, you can go to denied spectra that's defined from gathered from USGS website. You can define a site location of your building, and it will automatically reach out to USGS to get the target response spectra for you. Or you can do the UHS uniform hazard spectra, similar idea. But in this case, you can also use your own defined spectra, just to type in or upload a CSV file. First column is a period, second column is a SAVAC. And once defining this, you can also have a record selection criteria on the right, number of records, how many records you want to select, and from which fault type, strike slip, or you want reverse or non-stressed faults. And you can also specify whether you want to include the pulse-like feature and specify the earthquake ground motion that the recordings came from, how far the recording station to the earthquake source, because I don't really want Tohoku earthquake records to use that to analyze San Francisco's building, because the earthquake is really far field compared to the reality in San Francisco, which the ground shaking actually dominated by very close faults like St. Andrews Fault and Hayward Fault. And then you can also specify the ground motion characteristics like the VS30 and the duration. And so those panels can be also specified to help you constrain the ground motion selection and scaling. And then in the bottom here, you can also specify how you will select the ground motion. You can do no scaling, which is the roll records without any modification. You can do minimizing the mean square error between the mean response spectra and the target response spectrum. Or you can do a single period, which is, just confined or pinned at the target target period here, the conditional period. So everything set up, you can just click the selected records. And if your first time use this, then you need go to log in your peer accounts, which you can register a new one from peer website, and everything will be automatically dealt by the application once you click the select records to log in and submit to the target response spectra and download the records once the selection finished. So this is the ground motion event panel. So I will just following that, I will do a quick demo that's going through every panel here. I will think about like this could be event panel here. I just select 50 records, but in this same structural modeling part, I currently select one of the OpenSys model, which is the second example I will introduce in a minute. But I will do this demo with a simple structure like the MDOF system. I would say it's I will do a 5-story building. I have 5 different, and then I can specify different flow weights here. I can do story stiffness, and even for the story weight, I can just set it as a random variable, because sometimes I really don't know what's the exactly weights, and I have my material uncertainty like the steel strength. It may not be exactly 60 KSI or 70 KSI, so I prefer to also build it as a random variable here. So these two things will then identify by the application as a random variable, so you can specify it here. For instance, I will just specify a normal distribution with not a big standard deviation here. And for the yield forces, I will do also have a normal distribution here, or I can do a uniform distribution, just in the case that's having maximum and minimum value for that. And I can look into what's the PDF of this random variable here. And in the UQ panel, also the quantification panel, I have 50 records and also 2 random variables. So I want to do a lot of samples. So here I just do 50 sample just for the demonstration, but you can go really large samples, and everything will be handled in parallel in the backend. So you don't need, you actually, it's sort of optimized to help you to boost the computational speed. And then once that's set up, we have the UQ panel, we have this building model panel, we have the events, the ground motion we just selected. We also have our OpenSys file here, the solution engine, and then our EDP. And for EDP, I can use the standard earthquake EDP, which just to record the floor acceleration and the drift ratio during the analysis, and we'll report in the end. And I will click to run the analysis here. And this run button basically will send the job to the backend at the local, but you can also have the option to run at the design safe here. And I will, once you click on this button, there will be a login of your design safe account. And then you can also send the job to HPC, and once the analysis is finished, download the results. And this is the, okay, so this analysis is finished, and we arrived at this summary table. At every row, you will see one engineering demand parameter, structural responses, quantity, flow acceleration, peak flow acceleration, peak interstory drift ratio, peak flow displacement, and summarize the main standard deviation, skewness, and those moments information for you. But then you can also look into the data table itself. Here I have my random variable, 2 random variable, yield strength, just a sample from my distribution. And also I can know what's the events, which earthquake it runs. And for the responses, you can also plot different things. You can plot the CDF of the responses. You can plot a histogram here, and then you can also plot what's the data scatter between any two of the damage to look into. And if you want to do more post-processing, you can save this data to a CSV file. So I will just do a data example. And where I say, let me just save. Sorry, I just got. Okay, let's see. Let's just save that in the desktop. And then on my desktop, if I go to there, this is my example data file. So I will click into, and it's basically the CSV formatted raw data, and then you can proceed to do more post-processing if you following your own needs. And okay, so this is a quick demonstration, and the power of this too is that you can switch to different options for every step. You can use different modeling engines. You can use different earthquake events. For instance, you can do stochastic ground motion, which is you can provide the magnitude and the distance, and following this study. And then you can do user-defined earthquake records, just to submit a folder that's including all the records you want to analyze the building. And for the FEM panel, for the EDP, you can also do user-defined with some script. And we also have examples online, so you can look into the documentation and getting to us if you have any questions. But this is the one of the quick view of the use of EUQ that to help us to analyze the structure. But I will use maybe for like the next 5 to 6 minutes to just share one of the study I was working on, looking into the bridge column performance assessment, specifically under different earthquake scenarios, and using EUQ2 to help this research and show you some preliminary results. And So the bridge structure I look into here, I have one of the archetype bridge column designed with 24 feet tall, 48-inch in section diameter, and the column was designed to axial load ratio of 6% and 18 different number 11 grade 60 longitudinal bars, and the model the OpenSys model was built with force-based fiber elements, have 6 different 6 cross sections, integration points, and additionally having 1 zero length element at the bottom to count for the bond slip at the base of the column. And for the steel, it is modeled by steel O2, one of the sister resist model of the steel material in OpenSys with the fatigue material. For the fatigue material, it basically will calculate the damage index, give a strength history, and when the damage index reach up to 1.0, that indicates that the steel will get a fatigue failure, and the material will be broken in the analysis to reduce the stiffness and the strength of the column. And our interest responses or the responses are the peak column drift ratio, maximum fatigue damage index of individual bars. And the column itself we're putting into a site at Seattle, and Seattle is a very interesting city in terms of the earthquake scenarios that influence the community. It's sort of relatively distributed to 3 different sources. One is the crustal earthquake sources, which is contributed by the nearby Puget Sound faults. The second is the in-slab faults, and third one is the interface earthquake. And the last 2 actually come from the Cascadia subduction zone in the Pacific underneath the crust, underneath the ground. And looking into the contribution of those crust to about 60%, interface 30%, in-slab. And you will see the magnitude of the earthquake are quite different, and the site to earthquake distance are also very divergent. The seismic hazards for these 3 different earthquake scenarios are quite different. If I calculate the target response spectra, here's the conditional mean spectra for these 3 different seismic sources. You will see the interface one have relatively rich low frequency contents, similar as my crustal, but it has relatively less high frequency shaking intensities. And the in-slab one, just the opposite, it does have a lot of high frequency because it's relatively close to the site, and does not have that much low frequency long period influence. And the other very big difference between the 3 seismic sources are really the ground motion duration. Here is the 975 earthquake duration, 95 significant earthquake duration, and the interface one can be 96 seconds, so it's kind of like 1.5 minutes. And for the crustal earthquake, it's just about 14 seconds. So you can imagine that if I shake my building under a longer earthquake, the steel material can really be loaded, cyclically loaded much longer than the other case, and it has much higher potential to fatigue and fracture. And those potential failure is the structural engineer's concern about the bridge design, because Seattle is sort of a mixture of the 3 different seismic sources. So they want to know what's the behavior of the structure under different type of earthquake. You can see that if I really design for this interface earthquake, I really will be at a very high stand. But in the other hand, if I really design only for crustal earthquake, then my bridge can really fragile or really very vulnerable under those subductional earthquake. So in EUQ, actually, I use the user-defined response spectra, which I just show you in a minute. So I will do side by side for them. side by side now. It will be easier to see the things. Okay. So in the event panel, if I go to the PJ ground motion selection, I will use this user-defined target response vector to load a CSV file and to define the magnitude, distance, and the earthquake duration. And specifically for duration, I use 5 to 20 seconds for the Christchurch earthquake, 10 to 50 for the in-slab, and 50 to 200 seconds for the interface. And this mean upper and the lower bounds actually coming from the 3 standard deviation in the target distribution. And 50 records were selected for each scenario, nonlinear response history analysis conducted. And just to quickly fly through the user interface that loaded those information here. And for the EDP, I look into the damage index of individual bar. So from 1 to 9, it's actually just to do a half circle here. Try to get what's the maximum fatigue index of each bar here. And I also have the column drift and acceleration demand for global responses. And this is the raw result after analysis. And just want to have 2 summary slides about the results itself. Themselves. Then first I look into the peak lateral drift ratio on the left figure here. Different color corresponds to the 3 different seismic sources. So we'll see in terms of peak lateral drift ratio, the deformation demand. The bridge column tends to have largest deformation under the in-slab earthquake. The median value is about 2% drift ratio under the 975 design level earthquake for the bridge. And the Christchurch follows 1.8%, and the interface one is the minimum, the least deformed case. On the media, it's only about 1.4%. Well, the story is quite different and opposite when I look into the maximum fatigue damage that's in the individual bars. And here, x-axis is the fatigue maximum index, damage index in the column, and the y-axis just shows the probability of the cumulative density function. And in this case, the Christchurch earthquake actually caused very limited damage to the reinforcing bar. The media index only about 0.024, which barely caused any problem. Well, if I look into the other two, in-slab and interface, on average, the interface one is about 0.11 and the in-slab is about 0.10, which is starting to get the bar getting a finite number of fracture probability to occur. And so this study is quite preliminary, but the goal for this case is really to look into different earthquake sources, and EUQ2 is sort of help to differentiate 3 different tools and streamline the entire analysis process. And finally, I can get the response, this data, and do this post-processing to create the figures and to help structural engineers to assess the performance and improve the design. And the last figure I have here is about the fatigue index versus the earthquake ground motion duration. So there's no doubt there's a positive correlation between the two. So I also have different color for different earthquake sources. So you can see this trend more clear that actually under large drift ratio, of course, the fatigue index will increase, but you will see like the interface one is much on the top, and then followed by the in-slab and the Christchurch. And the major difference is actually coming from the earthquake duration there. And those example inputs and the results file are available in the Google Drive that's shareable for you. And you can, I will also share this slide in the end, so you can access to these files and directly load them in EUQ to test it out. And you can also do modifications and try different things as well. And hopefully this could be one of interesting example that you may have. And before closing today's presentation, just one final slide on the resources website. SimCenter of website, you will get the latest news, the recent release of every individual tools here, EUQ 2.3.2. And you can also access the application and the documentation from each individual tool page here. On the right-hand side, if you have any troubles using the tool, downloading the tool, or you want to introduce your own model to the tool and add more features into that, just feel free to leave a message on our SimCenter forum, and we'll reach out to you, get you back together more, and work together to make the tool better, and it can serve more people and more researchers to facilitate their own studies. And with this said, I will thank you so much for your attention, and thank you.
Thank you so much. Yeah, we'll now open it up to questions. Please feel free to just unmute and ask, or if you would prefer, you can feel free to share questions in the chat, and I or one of our co-organizers would be happy to read those questions off to Dr. Zhang.
I have a quick question. I noticed in the EEUQ app that some options doesn't have units that you have to include. So I would like to know if we need to track out those units that we are assuming, or if there is like if it's defined already, predefined the units that we include the information.
Yeah, that's really a very nice question. Actually, we're doing on this track in the latest release. So if I go into there, yes, so the units actually is quite first. One of the global units we define is in the GI panel. I'm sorry, I did not really dive into this in details, but in the GI panel, we actually define this global units. So anything that's in the output panel would really be in those units. Well, in individual panel, for instance, that if your model is really not configured, or it's in different units, then you probably need to convert that to the global units that you have. For instance, here in the OpenSys, you may build your model structure. If you build your model in SI units, then you may prefer to work back to have this to be SI units to be consistent with that. Or we're also working on the option that people can specify the units for each individual tools. For instance, here in the MDOF loop, we're trying to, because this tool is developed by one of our colleagues, and the standard units they're using is SI. So we want to convert their units to the specified units here. So we're actually doing this current working on this topic, and hopefully we can get them to the next release, so you can be unit free.
Oh, okay, thank you.
We have a question in the chat from Jasmine. How or in what part of the process is the local geology included in EEUQ simulations?
Yeah, that's a very good question. So local geology, I guess that would be, if I understand correctly, would be this local soil condition, and this part I will mainly contribute to the event panel. So here we have two, I think maybe two statistic or like a ground motion model that internally will consider the VS30, where you are getting the local soil velocity in the ground motion prediction model, which will influence your response selection. And for instance, you can go to the design spectrum, specify the site class here. But another very powerful tool that built in the EUQ is called site response tool here. I did not really get into the detail because it's have this earthquake topic in general, but this tool basically can help you to get, we actually have a second example in our tool that actually read a rock motion, and you can get the surface motion, and you can develop your own soil column here and specify the material property in OpenSys. There's a different hysteresis models that you can use to analyze the soil column responses and propagate the seismic wave from the rock base towards the surface, and use the surface motion to analyze your structure. That perhaps would be a little bit more detailed version of the local geology, and maybe you will use the depth to the rock to define the soil column. Maybe you would like to use the water pressure, water table, and to really use the shear velocity to do inverse problem to see, okay, what might be the right parameters to define those material properties to simulate the soil responses. Is that the question, or maybe correct me?
Oh no, that's a great answer. I didn't realize there were so many ways to put it in, but thank you for showing me. Yeah, thank you.
Yeah.
We have time for probably one more question, if anybody would like to ask one. I'll ask.
Sure.
Thank you so much for this. This was fantastic. I wonder, so I see that there are workable examples in the documentation for EEQ and SimCenter. I was also wondering if there are published examples, so publications that have used these tools, this one and others, successfully, and published work based on them. Yeah,
that's actually a fantastic question again. I think that we're actually getting people to start to use our tool in their publication. Recently, I think that one of the professor in Columbia used our EUQ tool for concrete structure design, and that's basically using, and he actually get us back and really introduce his modules, which I think that's it's not here yet, but will give us the reinforced concrete modeler in the tool here that other people can also use. And another example that's using EUQ is at Stanford University. Students actually using this in course project, and they actually look into the steel building model and try to analyze the responses there, and coupled with the damage loss assessment to develop better structure design that can be damage free, or like improve their seismic resilience under the earthquake. And that's kind of like one conference paper in the National Conference Earthquake Engineering. I think the author is Omar. I can direct you to that, to Omar, about the details. But yeah, we do actually having more and more people looking into our tool and consulting us about the use of that. So I feel like that's sort of a process. It's kind of like we have the developer phase, and now starting to get more and more users. You know, we can help more people. It's sort of most fortunate thing that we have. Oh, Kai, I think you muted yourself.
Okay, I think you're on mute.
My bad. So I do see that we have one more question in the chat, but I also see that we're out of time. I was wondering, will you take questions over email?
Sure, I can. Yeah, I can just do a snapshot, and maybe if you could provide the email address, I can also send the response to you. Yeah, can we apply correct correlations such as filters or line-based before the scaling to the Yeah, maybe I can just answer quickly. I think that the we do not really have this correlation model built in our EUQ, but we do have that in the R2D2, which we have the full package for including the spatial correlation and the interperiod correlation to construct the target response spectrum. But I can send you a full response to your email later. Thank you.
That sounds wonderful. Thank you. Thank you so much to everybody who attended today. Please know that we do have our next workshop will be, I believe, Friday, December 9th. Based on machine learning and AI resources using Jupyter Notebook, interactive data analytics, and high-powered computing. I will be confirming the speaker for that soon and then sending more information about that as well. But thank you so much to everybody who attended. This was a fantastic start to a really exciting workshop series. A huge thank you to our speaker, Quanxi Zheng from Stanford, and to all of our co-organizers for today. And we're looking forward to the next of these.
Thank you so much.
Thank you.
Yeah, thank you.
Thank you.
so much.
Thank you.
Thank you so much, Robbie and Ty and Jasmine and actually just for organizing and inviting me. Thank you so much.
We really appreciate it. And I will have this posted probably by tomorrow, but maybe this afternoon. I'm going to post it on the ECO YouTube. And then when I meet with Design Safe this afternoon, we'll talk about putting that on the Design Safe YouTube as well.
Sure. Thank you so much. And let me know if you need like any other things or need me to look into the transcript anytime. Pleasure.
All right. Thank you so much.
Thank you.
Thank you.
And if there's
Take care.
anything you want to send to follow up, we're happy to circulate slides, workable examples, anything after the fact.
Sure, sure. I can send the slides to the final version to you, and just if anyone asks, you can share them.
Sounds good. Thank you.
All right, thank you.
All right. Bye-bye.
Bye now.